Hello and welcome, class, to another lecture wherein we will be discussing Bronsted-Lowry definitions for acids and bases, as well as then water, the solvent, and the pH scale. There is a lot that we're going to be talking about today. So part 1 is, again, really just a review of Chapter 9's basic definitions of acids, bases, and pH. So if you have not gone back to rewatch that lecture, please take a break and do so. It can be found in the fall of 2020 playlist here on my channel. So again, Chapter 9, the acids, bases lecture, that is going to be the part 1 to this series. Part 2 here, we're going to just, again, push it a level deeper. So we're going to revisit what it truly means to be a Bronsted-Lowry acid and base. In addition, we will be touching today on the impact that water as the solvent has on acids and bases in terms of strength, as well as how it is the solvent that defines and determines what the scale for our pHs are going to be. So let's just jump into it. All right, so the definition of a Bronsted-Lowry acid and base as defined in Chapter 9 was essentially an acid donates H plus to solution and a base accepts H plus from solution. However, the true definition of Bronsted-Lowry acids and bases truly is just that nothing is inherently an acid or a base. Instead, these things, acids and bases, have to occur in pairs. There is going to be an acid that interacts with a base, where it's the acid that transfers the H plus to the base. You can't have an acid without a base, and you can't have a base without an acid of some sort. So because these two things occur in pairs, where the H plus is what is being donated from acid to base, we can also say that the transfer of this H plus from acid to base is going to be occurring in some kind of dynamic equilibrium for a majority of acids and a majority of bases. All right, so here we can see the generic definition of an acid and a base coming together, and we can see it's the acid and the base that are going to be present on the reactant side. And again, the H plus is going to be what is donated from the acid to the base. The acid is the H plus donor, the base is the H plus acceptor. After the H plus has transferred, though, from the acid to the base, on the product side of the reaction, we can see what is written here as something labeled as a conjugate base and something labeled as a conjugate acid. Now, conjugate base is really the product form of the acid after it has lost the hydrogen, so minus this hydrogen to give us something now that has a partially negative charge. And similarly, the conjugate acid is going to be the product form of the base, where this base has now gained an H and should have a charge that is higher, or a plus charge, compared to the basic form. In essence, conjugate bases and acids differ from the respective reactant acids and bases by only a single H plus. The reason why we say that the acid and base coming together reacts in dynamic equilibrium is because now on the product side, we again have a base and an acid that can interact with each other. Now, the product shifting back towards reactant may not be as strong, as the H plus is going to now shift from this conjugate acid back over to the conjugate base. However, this is still somewhat likely to occur, all depending on the relative strengths of the acids and bases on the reactant side. We may end up with a reaction that is truly reversible, or a reaction that is not reversible at all depending on the relative strengths. So let's look at a couple of more specific examples so we can get a feel for what this means, what acids and bases are, in addition to what the conjugate pairs of the bases and acids are on the product side. All right, so in solution, if we have a weak acids are known to produce weak or conjugate bases. So a conjugate base, as we can see from this example reaction below, is the product of a weak acid dissociating. So our weak acid in this hypothetical case is HSO4-. This is our weak acid. In solution, so if we're assuming this is right in water's taking part, accepting an H plus from this weak acid, we can see as the dissociation occurs, we have a H plus in solution. This represents our H3O plus here. And now we have an SO4 2 minus left over since the hydrogen has moved onto the water. Now this reaction, as we can see by this arrow here, is reversible. So this SO4 2 minus, if we were to look at this reaction from the opposite perspective, right, products become reactants, this SO4 2 minus is able to interact with the water reversibly to create some more HSO4 minus and some OH minus. So we've talked already the reversible nature of the dissociation of these weak acids and weak bases. They're always going to be interacting with water. Because of the water being the solvent, we're always going to have a little bit of H plus and OH minus. So the presence of this H plus and the OH minus in solution simultaneously should not be surprising, though it is sometimes strange to look at because we think of these two things neutralizing. When they neutralize, we just get more solvent, we get more water. So in solution, we have this weak acid interacting with water, dissociating into a weak base. A weak base that is the result of a weak acid, which in this case we are labeling as the reactant, right? The weak acid is the reactant in this first reaction. A weak base is the corresponding product. This weak base then becomes known as a conjugate base. The existence of this base arises specifically because of the weak acid dissociating. So this weak base now is going to interact with the water and recreate some of this acid, which is going to then be in the first reaction, dissociating to create this weak base. We have this back and forth, right? Again, this is the reversible nature of this weak acid dissociation. So the conjugate base of a weak acid is also the base that leads to its conjugate acid. These two pieces, the acid and the base, are intrinsically linked in solution because of the reversible dissociation in water. So when I say conjugate base, what I mean is the weak base that is the result of the weak acid dissociating in water. And similarly, because again, we have this reversible reaction, this reversible nature, a conjugate acid is the result of the weak base in solution. So in this hypothetical example, we have ammonia. This ammonia is going to interact with the water, and our ammonia is going to behave as a base. It is going to accept an H plus from the water, which is exactly what we see on the product side. An H plus has left the water, has moved onto the ammonia, giving us the ammonium ion, this NH4 plus, and this leaves us with hydroxide left over. Now this ammonium ion is connected to the ammonia because they are only different by one H plus, right? If it has the H plus, it is the weak acid corollary. If it's missing that H plus, it becomes the weak base corollary. But this is what we mean by a conjugate system. A weak base is going to lead to a conjugate acid, and a weak acid is going to lead to a conjugate base. It is the resulting base or the resulting acid from the dissociation in water. So it definitely seems like the solvent itself, the water, is going to play a role in the the strength of the acid, the strength of the base, since the water is a reactant in this reaction. So the impact of the solvent is going to be that your solvent will define what your quote-unquote pH scale is for acid-base strength. Now we are assuming here that we are not undergoing a true neutralization reaction yet. We're just taking an acid and dissolving it in water, or taking a base and dissolving it in water, where the water is going to act as the corresponding base and or acid respectively. But we can see in this chemical reaction down below that even if we don't have an acid or a base present, water is going to be able to react with itself reversibly, where one of these waters is going to reach out and take an H plus from the other water that it is next to, giving us H3O plus and OH minus. Now, this dissociation between water molecules is what defines what the acid is in solution. The acid is H3O+, as well as what the base is in solution, because our base is going to be OH-. In fact, because water is our solvent and water is going to be interacting with the things that we label as being acids and bases in solution, the conjugate acid of water, being H3O+, is the strongest acid that we can have. Similarly, OH-, which is the conjugate base of water, is the strongest base that we can have in water. This is a part of the reason why acids such as HCl, for instance, or bases like NaOH end up being defined as strong acids and strong bases. It's because these things donate nothing but H+ or OH- to solution, which, because our water is the solvent, these things are defined as being strong acids and strong bases. Like, if the acid matches the conjugate acid of your solvent, or if the base matches the conjugate base of your solvent, these things will be defined as strong. So the HCl, the NaOH, and the other strong acids and bases we'll be talking about and defining a little bit more in detail in our next lecture. So we will be returning to this, but for right now, we're just going to focus on the impact of the solvent itself. Like, if we just look at pure water, what does pure water and its dissociation, illustrated here, tell us about the pH scale? Like, how does it define what the limits of the pH scale are through the presence of the conjugate acid of H3O+ and the conjugate base of OH-. All right, so if we have this dissociation occurring in solution, or even in just a pure sample of water, we have a measurement available to us. Again, the pH of pure water is 7. This 7 tells us a lot about what is happening in solution, and it defines fundamentally the boundary of our pH scale being 1 to 7. So let's just start with what the pH of 7 is telling us about the nature of the solution, and then we will build ourselves up to the scale being set between 1 and 14. So the equilibrium constant of pure water at 25 degrees Celsius, or room temperature, is something that we are able to find just from knowing that our pH is equal to 7. Since this is a reversible reaction, the simplified version I have here, just the form that's looking at the alleged decomposition of our water into H+ and OH-, we can write an equilibrium constant, a Kc, representing this decomposition, since it is reversible, right? Any type of math that we want to do with this reaction, whether it be measuring concentrations or, alleged theoretical yields, because this is a reversible reaction, we have to work with an equilibrium constant. It's not enough to use stoichiometry. This reaction is reversible, meaning that we have to use some type of equilibrium constant and equilibrium constant expression. Because the reaction we can see here is a heterogeneous reaction, right? We have water that is in its liquid form, and it is breaking into two aqueous pieces. When writing the equilibrium expression, where it's going to be a ratio of products divided by reactants, once again, our only reactant is in a form, right, a liquid phase, that is not something that we ever include in an equilibrium constant. Because the density of H2O is constant, we don't have to include it in any type of equilibrium expression. So the ratio of our products to reactants ends up looking very similar in this case to the KSP examples we just looked at on Friday. When we're looking at solubility of some type of solid, we only ever looked at the products, the ions that were the result of the soluble or mostly insoluble substance being added to water. Here we're looking at something very similar. Water is a liquid, don't have to include it. We're just going to look at the balance of the products that are here. So our Kc, the equilibrium expression for water, is oftentimes notated using this very special K sub W, where W just means that we're looking at water. That's it. Kc of pure water is known as Kw. And the reason why we have this notation for a very special Kw is because everything acid-base related, all of the pHs and the pOHs and the pH scale, it's all defined by water and water's nature. So we are going to gift water this very beautiful and special present that it has its own unique equilibrium expression, its own unique equilibrium constant. Now the equilibrium expression is going to be equal to the multiple of the concentrations for H plus and OH minus. No exponents are necessary since we see that there are just stoichiometric coefficients of 1 in front of the H plus and 1 in front of the OH minus. Okay, so if we want to figure out what this special equilibrium constant is and how it gives us some information on the pH scale, well, we first need to know what the concentration of H plus and OH minus is, right? We need to figure out what this equilibrium constant value is equal to. And as I said, knowing that the pH is equal to 7 is enough to figure it out. All right, so let's see how the pH of 7 is going to come into play. We are working with an equilibrium expression, and if we are set to find equilibrium concentrations from the information given to us, if we set up some type of ice table, we will be able to find these equilibrium concentrations. Now, water, again, is a liquid. Don't have to care about it. Just blocking it out. We're only going to be looking at the H plus and the OH minus. Now, if we assume a time equal to 0 before the dissociation has occurred, right before we have any type of product, if we look at the reactant, we see that we only have H2O plus initially before the reaction starts. This means that we have no H plus and no OH minus, since in the wording of the problem, again, nowhere is it listed. Nowhere are we told that we have H plus or OH minus initially. Now, there will be problems where this will change in the future, but for now, again, no H plus, no H minus initially. In order to reach equilibrium, then, this reaction is going to have to shift from reactants to products, giving us some additional X, some change in the product direction. At equilibrium, therefore, that means that we are going to have X amount of H plus and X amount of OH minus in the units of molarity. Okay, this is cool. We now have an equilibrium expression that we can't solve because we don't know the concentrations of H plus or OH minus. Or so it would seem. But again, we have this pH value and we have yet to use it. So let's see where this is going to be useful. pH, whenever we measure a pH measurement is at equilibrium. So the pH equal to 7 is a measurement that is at equilibrium. We have nothing to start with, and so if we were to take this negative log of 0 to give us a measurement for pH, it's nonsense. We don't have anything there. If we wait until we reach equilibrium, well, now we have an H plus concentration where a pH is going to be meaningful to us. So this pH equal to 7 can be used to find what the concentration of H plus is at equilibrium. Now, if our pH is equal to 7, our concentration of H plus that was used to find that is equal to 10 to the negative pH. In other words, the concentration of H plus is going to be equal to 10 to the negative 7 molar. So the pH that is equal to 7 tells us that at equilibrium, once this water has settled into its own inherent nature, reversibly reacting, creating some H plus and OH minus, the H plus concentration is going to be equal to 10 to the negative 7. And as we have seen before in this type of problem, X is equal to X, right? There's nothing special about one X being H plus and the other X being OH minus. So if we now know the concentration of H plus is 10 to the negative 7, this tells us that the concentration of OH minus is also 10 to the negative 7 once we have hit equilibrium. And so these are the values now that we can plug into our Kw, our equilibrium expression for water. Right, 10 to the negative 7 concentration in the units of molarity for H plus, same with OH minus, giving us a 10 to the negative 14. So it's kind of surprising. We have one pH measurement, and that one pH measurement was able to tell us what's the concentration of everything that's in solution, as well as what is the equilibrium expression, what is the balance of H plus and OH minus in solution when our baseline for any type of solution is this water, the solvent that is going to dictate the nature of everything else. In other words, anytime we add an acid or a base to solution, this is the equilibrium that we are fundamentally altering in some way. And so this is how the 10 to the negative 14 equilibrium constant is going to set our pH scale. Explicitly, we're going to see the math in a couple of seconds, like where the 1 and 14 come from. But this is our setup. Anytime we add any acid or base to solution, we are fundamentally altering the concentration of H plus or OH minus in some way. But as we have learned, an equilibrium constant is a constant so long as you are at the same temperature. This 10 to the negative 14 is going to dictate, as we alter pH and pOH, what is the boundary, what is the limit to which we can alter one versus the other, since the two are inherently linked in equilibrium through the solvent being water. Okay, so let's explicitly see where the pH scale then comes from. What is this 10 to the 14 or 10 to the negative 14 explicitly and mathematically tell us? Okay, so let's set up the scale. We now have an equilibrium constant representing the balance of H plus and OH minus in water. We also have a means to represent both the H plus concentration and the OH minus concentration on a logarithmic scale. So let's do that here. Let's shift this equilibrium perspective, this equilibrium expression, into something that is more familiar on a logarithmic scale. So we're going to take the negative log of both sides of this equation. The negative log of our Kw is going to be equal to the negative log of the concentration of H plus times the concentration of OH minus. And this may not apparently at this stage seem to be useful to us, but one awesome property of logarithms is that if you have the log of two multiples, like two things being multiplied together, this is equal to the logarithm of the first piece being added to the logarithm of the second piece. So here now we have the negative log of H plus being added to the negative log of OH minus. This is equal to the pH plus the pOH. Now the negative log of Kw is also something we can explicitly solve for, since Kw is a constant. So the negative log of Kw is going to be equal to the negative log of 10 to the negative 14. This was the value we just solved for. And here we can explicitly see where the cap of our pH scale comes from. The logarithmic nature of how we measure concentrations of H plus and OH minus is exactly where the 14 comes from. The balance of H plus and OH minus in solution being set to this 10 to the negative 14 is no coincidence. It is how we measure numbers. It is the nature of water itself that we are observing, and the nature of water sets our cap of the pH scale to 14. So if your concentration of H plus is going to be of a certain number, giving us a pH, let's say, equal to 1, the OH minus concentration has to obey our equilibrium constant expression. And how we represent this using pH and pOH is that the remaining concentration here of our OH minus has to sum together with the pH to equal 14. This tells us that our pOH has to be 13. Both of these numbers then also tell us what the concentration of our species is. The concentration of H plus in this hypothetical example will be 10 to the negative 1, and the concentration of our OH minus is going to be 10 to the negative 13. This again balances with our equilibrium constant being 10 to the negative 14. And if all of these numbers, keeping track of all of them, is confusing, well, here I have a chart or a graph, a map that connects all of these pieces that we have talked about so far. The concentration of H plus is going to be oftentimes what we are the most concerned about knowing. If we want to find the concentration of H plus, well, either we're going to have to know what is the pH. This is something that we can measure. And then using the equation of pH is equal to negative log of H plus, we can figure out what the H plus concentration is by rearranging and solving using our pH. However, if we also know something about the basic component of the solution, because our solvent is water, we can use the equilibrium expression for water to also figure out what is our H plus concentration if we know the OH minus piece. Or if we know the H plus piece, we can use that with the Kw for water, right, this equilibrium expression to find the OH piece. Since these two concentrations, these two species in solution are inherently linked because of the solvent we are working with. Now we can also find the pOH in much the similar way, the OH minus concentration working with the pOH, but if we know the pH or the pOH, we can use this second form of our expression, our equilibrium expression, to relate these two pieces together. So this flowchart is not anything you specifically have to memorize. Figure out what type of math works best for you, but this will be at your disposal, available to you. In fact, I have attached a PDF or uploaded a PDF to Blackboard that has this chart on it. Not that you can't pause the video right now and write it down, but there is also that PDF that is free and clean and available to you, to download or use whenever you need to. All right, so let's look at an example problem that links these pieces together, the pH and the pOH. What are the values then of the concentration of H plus and the concentration of OH minus in an aqueous solution of NaOH that has a pH of 11.7? So here we are looking at something that is very basic, right? Your pH concentration is more towards the 14 side, meaning that you are working with a base. This makes sense since sodium hydroxide is a very well-known strong base. So there are a couple of different ways you can go about solving for this problem. First, we can use the pH to figure out what the concentration of our H plus is. This is the first and most inherent, direct link that we can see. Right, and the concentration of H plus is equal to 10 to the negative pH, or 10 to the negative 11.7. When calculating this value, this gives us a 2.00 times 10 to the negative 12 molar. We can see that this is a very small concentration. And there are two different ways now we can solve for the OH minus concentration. The most straightforward way would be using our equilibrium expression, which gives us the balance of H plus and OH minus in solution. Our Kw is 10 to the negative 14. The H plus concentration we just solved for was 2.00 times 10 to the negative 12. We're going to multiply this by our unknown concentration of OH minus. Now, if we rearrange and solve for the concentration of our OH minus, this gives us a value that is equal to 5.01 times 10 to the negative 3 molar. And this balance between the H plus and the OH minus that exists in solution, due to the reversible nature of our water being present, now we can see that we have offset the scale. Right, in neutral water, the concentration of H plus and OH minus is equal. Now that we have added some extra OH, the concentration of our OH minus goes up, and the concentration of our H plus goes down. We are functioning on this seesaw here. If one goes up, the other has to go down. Relative to when we are balanced, the value is equal to 10 to the negative 7 molar, equal to 10 to the negative 7 molar. If our concentration of OH minus goes up, which is exactly what we see here, this is greater than 10 to the negative 7, our H plus concentration is going to go down relative to that 10 to the negative 7 value. All right, the other way that we can solve for this problem, or solve for the concentration of OH minus specifically, is since we have a pH, we can find a pOH, which is equal to 14 minus our pH, and our pOH is going to be equal to 2.3. To solve for the concentration of our OH minus, this is equal to 10 to the negative 2.3, which is exactly equal to 5.01 times 10 to the negative 3. Regardless of the approach that you take, whether you find the pOH first, or if you use your equilibrium expression to directly solve for your OH minus concentration, you will find the exact same value. And again, that is because all of the derivatives that we did today, all of the algebra that we did today, is all self-consistent. We used one problem, one mathematic expression, right? pH is equal to negative log of H plus to define everything else afterwards. So all of this math will always be self-consistently true. If you use two different approaches and you get two different answers, like when you're solving for this OH minus concentration, for example, chances are it's because the math somewhere went wrong. Not that the derivatives themselves are bad, but that either you miss a negative sign, you miss a parenthesis, so always be kind of double checking your work like that. All right, last but not least, it's going to be important for us since the pH and the pOH, or the H plus and OH minus concentrations are like always going to be in balance. In water, we have to look at all of these sources of H plus and OH minus in order to solve these problems sometimes. This is going to be most emphasized when we're working with dilute solutions. In other words, when we have very few solute particles in solution. For example, if we wanted to look at the pH of a 4.77 times 10 to the negative 8 molar solution of HCl, we would assume, even without doing any type of calculation, our pH should be less than 7 since HCl is an acid. So let's double check this, right? What is the pH when we take the negative log of 4.77 times 10 to the negative 8 molar, since this is apparently the H plus concentration that is coming from our HCl here? Well, if we calculate the pH from this concentration that we're immediately given, it appears as though our pH is going to be 7.32, which is greater than 7, which is going to give us a big old question mark here. How can the pH of an acidic solution be greater than 7? And the answer is, it can't be. We're missing something. And what we're missing is the acknowledgement that not only do we have HCl in solution, we also have water. And as the water breaks apart into the H plus and OH minus components, this H plus from the water directly is also going to have an effect on the pH. So let's learn or look at how to solve for the H plus concentration in a dilute solution when we have such a small amount of solvent that apparently our pH is going to be incorrect. The entire connective thread of this lesson so far has been that anytime we add an acid or a base to water, what we are doing is affecting the balance of the H plus and the OH minus as they dissociate from pure water in its liquid form. All right, so what this means is that if we are looking at the balance now as we have changed some type of condition, what is our new equilibrium condition going to be from the perspective of this water as it is decomposing? All right, so what we have here is a solution of water that was allowed to reach equilibrium and then was disturbed by the addition of some extra HCl. In other words, we are going to add this concentration into our initial component, our initial kind of category here underneath the H plus. And again, just to reemphasize, the reason we're doing this is because we have assumed that water in its pure form had reached equilibrium, and now we are changing the equilibrium. We have disturbed the equilibrium in some way by introducing new initial conditions. This is going to help us out mathematically in the long run. The OH minus concentration, we are assuming that we didn't disturb this initially in any way, right? We didn't add any NaOH when we were disturbing the equilibrium. We only added HCl. So let's look at how the initial presence of H plus here from the HCl is going to affect the balance of equilibrium. Now we can see that we are still going to have to shift from reactants to products here since we have no OH minus initially based on this change in conditions. So we're going to get a shift by some amount x towards the product side. So we're going to end up with 4.77 times 10 to the negative 8 plus x for our H plus concentration and x for the OH minus concentration. Now again, this makes sense if our perspective is we have added some H plus, which is what this 4.77 times 10 to the negative 8 represents, And the water is also going to contribute some H plus and OH minus once it has reached a new equilibrium. So the equilibrium values for X can be found by setting up our Kw equal to concentration of H plus and OH minus. The H plus concentration is going to be that 4.77 times 10 to the negative 8 plus X, and the value for OH minus is also going to be X. Okay, so if we want to solve for what the X is going to be equal to here, what we're going to do is rearrange and solve for our X as is presented. So we can set up a 4.77 times 10 to the negative 8 X plus X squared by distributing this X in. And our Kw, which is equal to 10 to the negative 14, we can also pull to the other side, minus 10 to the negative 14. Now, using the quadratic formula, we can solve for what X is equal to, and X is going to be equal to 7.90 times 10 to the negative 8 molar. All right, so this change, this difference in our X is going to help tell us exactly what our new concentration of H plus is going to be at equilibrium. We're going to take this X, we're going to add it to the concentration from, or that's the contribution of our HCl, and then we are going to calculate what our new pH is going to be equal to. So taking 4.77 times 10 to the negative 8, adding it to 7.9 times 10 to the negative 8, this is going to give us a new H plus concentration at equilibrium that is equal to 1.27 times 10 to the negative 7 molar. If we want to calculate the pH, which is what we are charged to do, right, we're finding what is the pH. pH is equal to the negative log of 1.27 times 10 to the negative 7. And this is going to give us a pH now that is slightly acidic, 6.90. All right, so I did admittedly speed through some of the math after we have set up our equilibrium expression here. Again, anytime you need to pause these videos to kind of catch a break, absolutely catch that break. I would also encourage you to practice the math down here, solving for our X using those quadratic equations. Make sure that your X value is equal to my X value, because when it comes to taking tests or working through this type of math on your own, I want to make sure that you get that practice under your belt. Again, to emphasize, practice, practice, practice. And that is going to be our lecture for the day. So throughout today's lecture, we have seen that Bronsted definitions, the Bronsted-Lowry definitions for acids and bases, are a little bit more involved and definitely take place in reversible conditions. We have seen that the acidic and the basic properties of water as it dissociates with itself are going to be what define the pH scale. And then we looked at how we can calculate pH and pOH using this scale. All right, so here we have some section review problems covering each of those topics, just identifying different Bronsted-Lowry acids and bases, as well as observing the pH properties of water, in addition to the pH and pOH scales. So if you'd like some extra practice, please go ahead and get some practice. When we come back to our next lecture in part 3, we will be returning to acid-base strength, but more focused on the structure of the acids and bases themselves. So now that we have talked about the impact of the solvent, being water in our case, we can turn our attention to the things that we define as acids and bases, things that have more of an impact on the pH of solution. All right, but for now, if you have homework, please double check and do your homework. If you have any questions, do not hesitate to let me know. And until next time, class is dismissed.